I see people are slowly but connecting. Because on the YouTube already 12 people watching now. So hello everyone who is connecting, who didn't get demotivated after yesterday's lecture, who still has some interest. So hopefully today is going to be even better than yesterday. Meanwhile, we are waiting for the others. Maybe you guys have more questions after yesterday, more reflection. And also I saw there are some questions in the chat and I'll answer them right now as well. So we can say hello to each other, ask questions, complain about something, etc., etc. Okay, it's 10 now. I think let's wait not more than 3-4 minutes then for other people who are still coming. And let's spend this first minutes for the questions from yesterday, right? So did anyone try to launch the code? Did anyone try to check the slides? Maybe Google something about it, or at least rerun the code, maybe even apply your own data with this code. I'm just curious, or you didn't have time yet? Seems like everyone was pretty chilling yesterday, right? Guys, at least let me know that you're alive, because I see that there are people viewing the YouTube, but I don't understand if it's just like some random people connected and they're going to disconnect in 1 minute, or basically you're already here and you're ready to start, because I also need at least some little feedback from your side.
I'm sorry, I just gave the wrong link, I think, to the Slido, but I already updated. So everyone who is in YouTube has a new link. And there was one hello.
Hello, that's I'm the one who said hello. I'm just trying to engage people.
Okay.
Didn't have time yet. Yeah, it's fine. I'm just curious. Maybe someone got motivated. All right, then. I think I'll just start with a small, short review of what we were doing yesterday, just to remind you basically the topic we're in. We discussed that there are people who are playing different roles in the finance sphere, and they're not all of them are like traders who are buying stuff that grows at the price. They also support people, the people who create such investments instruments, etc., etc. And they separate as a front office, back office, and buy side, sell side. We also discussed that there are different apply directions, and for simplicity, we divide them into banking, where banking is something that is relatively simple. The data is straightforward, and in asset management and trading, the data is a bit more complicated. We also discussed a bit that when we talk about the project structure, when you want to create like a trading system, that is like the full cycle from the research ideas to the actually executing engine and supervision stuff, we need this sort of squad. And what we learn in these 2 days is mainly related to the people who are like defining the features and doing the strategies. We also discussed more applications in finance, and also what was, I think, relatively interesting, we discussed some trends that are appearing in finance lately, and they're related to the nowcasting, for example, and we checked that there is some data sources that can allow you to not to do some forecast for the future of the time series, but if you have access to some interesting intermediate variables, you can actually track the state of the market. And for example, we saw that the copper supply chain fell much before the market falls. And if you could combine it to the coronavirus epidemic in China, we could actually predict some market crashes. Also, we saw that in finance, you want to develop theories, not just around the backtesting. So this is like interesting insights about the field and what practitioners are talking about it. Then we discussed a bit financial data structures. And again, we reminded here that there is data that stays the same all the time. It's not stochastic, because information about the clients is always information on the clients. A transaction is always a transaction, and transactions is for $100. It's not random. It's always been transaction for $100 from person A to person B. While in time series, it might be a bit different. We also saw that there is data like from the images, news, and it might be a bit harder to process because of the algorithms we need to apply. But in general, this data is more or less not random. Basically, if the sentiment of the news is positive, it means it's positive. And then there is market data and financial fundamental data that is actually described as stochastic processes. And the price of $100 per share, by itself, it says nothing. It can be meaningful only in the large context, as a part of the big complex distribution, and that's what we are trying to model in this field. And the same with regard to the outputs. Some of them are easy to predict and to work with, some of them are harder. We also discussed the framework of the portfolio optimization. We treat it as basically the baseline part when you want to invest your money. First, you're looking for something what is relatively stable, explainable, predictable, what serves as a proxy for the market to choose for yourself. And we discussed that, okay, you want to first choose the assets that are calm, that are growing, that can be diversified, it's like your trading universe. Then you also want these assets to be, let's say, their growth and the behavior, you want it to explain with some factors or some variables. Then you diversify it, you select the metric to optimize, and when you build a portfolio, obviously you want it to work as well on the out of sample data in the future. And we discussed that, okay, the returns, basically the change of the price, is how we measure the profit. Variance is one of the risk sources, because the more volatile, the more variant time series is, basically the more complicated it is. We discussed a couple of models that basically they're like linear regressions. They're just simple linear models that can predict return based on some factors. We can see that in the Fama-French model, the factors are the market growth, the size of the business, and the value of the business. So basically based on this, you can predict the return, supposedly. We also discussed different allocation schemes. And we also discussed that normally we want to optimize with some risk-adjusted returns. We also use some classical approaches that basically all what we do is running some optimization process. We can minimize the risk, we can maximize the Sharpe ratio, we can maximize the diversification, we can actually build combination of many others target functions that we want to optimize, and we can even combine them. That's what we saw. We also checked out that we also want to track a bit more other metrics. We want to track information ratio, drawdowns, and some advancements over Sharpe ratio that basically are making correction for the multiple trials and not normality of the returns, because this is important. We put it together into different strategies, and we saw, for example, that we can optimize for variance, Sharpe ratio, etc., etc. But also what we saw that when we want optimizing, for example, for the maximal Sharpe ratio on the training data, or for example, if we're maximizing returns on the training data, it performs really, really bad, or at least worse than expected on the test data in the future. So we came to the idea that we need to do some sort of regularization, just as we do in normal machine learning. And then the regularization, we discussed that it can be imposed, or for example, adding more data. And okay, we can't add more data because we have like fixed years of trading, but we can increase sample frequency. So instead of having the daily prices, we can have hourly prices. So this way you have more data. Or we can decrease number of parameters, which is regularization of itself. Or we can impose some structure that also reduces number of parameters, which is also a regularization by the structure. And we saw that, for example, the simplest way to do it is to apply the constant correlation model, but obviously it's oversimplification. So we learned about the shrinkage, where we can regularize the sample covariance matrix as risk sources with some even very simple model as the constant correlation model. But when we mix them, we regularize the sample covariance from the training data with some model. So this way it's more stable, and we actually saw it, how it works. We also learned about hierarchical risk parity model. We also checked some alternative methods how to find the proxy for the market based on the reconstruction of the data, both PCA and autoencoders. And we saw that they work actually differently from the hierarchical risk parity or other models. We ran these portfolios. We did some improvements, and we also realized that all what we did there is some sort of the proxy to your market. So basically you chose a lot of assets and you found the optimal policy, what is kind of, let's say, safe, predictable policy, how to allocate the money on these assets. But what you actually want to do, you want to have the, let's say, you want to perform better than this proxy. You want to outperform the proxy. You want to have some additional data sources so you can predict something in the future, be more efficient. So that's why we decided that, okay, we can leave something in this, let's say, proxy or baseline portfolio, and some part of our money we want to allocate to the strategies that actually look to outperform. And we check a couple of more examples with Black Litterman portfolios, if you remember, but yeah. And today, basically, we want to dive into the field of exactly making better than the baseline. So we will discuss active investment management with machine learning. So basically, this is like the core thing of the course. And the emphasis of this day for us will be comparing how, so to say, Kaggle machine learning is very, very, very different from the financial machine learning, because as I said you yesterday, the models here don't really matter that much. How you treat the data is much more important. And we will do several practice sessions. We will do iterative improvements. And in the end, hopefully you'll get deeper understanding where in finance you can just run some boosting model, deep learning model, and expect good performance. That's what we're gonna do today. And in the end, I want really to discuss like much more things about like future directions, what you will need to study, how you can build a career in this field, etc., etc., etc. All right, if you're ready to start, I'll check again if you maybe have some questions. And if we don't, we'll be good to go. Hello. Could I know who uses your automated trading systems? AI-based trading systems, where can I use it? Basically, right now, my automated trading systems are shut down. So no one is using them at the moment because they need, let's say, polishing the work over them. And in the current market situation, the ideas basically to discuss, there is market analyst who's creating the ideas first. And the systems are based on the ideas that were active, that were working more than 1 year ago. Now these ideas are not relevant to the current state of the market. So basically that's why the project is stopped, because we have a bit different priorities at the moment. So basically, yeah, also when you build such an automated trading system, it doesn't mean that you code it once and it works forever. It needs to be constant research and check and experiment, getting and acquiring new data sources. So that's why it's constant work. So my systems are shut down. There are 2 questions in the chat, and I also want to answer them. Anna Kornichuk asked about operational risk analysis, and she can't find any data set to work with. And she's asking if we can use Bayesian networks for decision support for operational risk analysis. Unfortunately, I'm not the expert in operational risk analysis. I imagine what it is, but I think this is the field where you really want to rely much more on the mathematical models. And Bayesian, because you don't have like a lot of data here, because in finance you have a lot of market data, and operational risk is something what is related to the company, and the data might be or not present or not organizable, etc. So I think you want to look forward into mathematical models that can be calibrated with some empirical data, and Bayesian networks is basically one family of this kind of models. You define the causal relationships and feed them to the maybe even small amount of data you have. Also, Vladislav Shavkove asks about what are advantages of such technique as autoencoder for outliers detection over well-known statistical approaches like 3 sigma or something like this, except the ability to detect multivariable outliers, which IQR is not fully capable of. Basically, the idea is, you're right, that it's not just about multivariable outliers, but it's about curse of dimensionality. Because statistical approaches, they fail horribly when we are working in the dimensions of already of the dozens or the hundreds. And the autoencoders, what they do, they basically learn the efficient mapping from high dimension to low dimensional data. And actually in the representation of the autoencoder, you can use your IQR approach really, really well. So basically what autoencoder does for you, it reduces the dimensionality and unlocks using of classical approaches on the high dimensional data. I see there is no new questions so far, so I'll keep going with the slides. Why financial machine learning is different? And as the headline of the section, I want to say that prices are not pixels. Yesterday also we wanted to talk a bit more about the econometrics. So that's why I want to also share my screen and show you slides of Marcos Lopez de Prado on econometrics, because yesterday it was one of the most upvoted questions. So this will be good to have a look. Basically, as you can see, basically, you know that financial problems are most probably beyond econometrics because of complex relationships that are not linear. And we saw that Fama French model is linear, and real relationships are like hierarchical and not linear. Most of financial data isn't structured, is text, images, recordings. It's basically the prices that you see on the market. It's just the result of the financial activity. So that's why you can't really rely on this so good. And also curse of dimensionality. And econometrics, it relies on the p-values, which are basically, in a way, not working anymore. You can check it by the link. The econometrics models, they, as many other mathematical models, they're designed to explain variations in data in sample. They're not designed to forecast anything. Even that Fama French model we saw, it is designed to explain returns on the trained data. So basically econometric models, they're not working in the future. Also, they rely on the assumptions like market efficiency or market neutrality or something like this that basically are just assumptions that are maybe not really present in the real world, and many, many other things. Yeah, basically, and as a result, we can see that most of the econometrics is just linear regression with some features. And it was done by many scientists. And also you can see the Econometric Society influenced a lot by biostatistics, where actually predicting something in the future is also not the key things. And let's walk shortly through the pitfalls. As we saw, econometric data is basically structured and not interesting, because as we saw with the annual inflation rate, why you want to wait yearly to wait for some report from the government or from the bank if you can track this data in real time from Amazon? Basically, these financial variables that are being released every month or every year are simply not interesting. And real world data is a bit in real time, it's much more complex. Also, we discussed yesterday a bit on the correlations. Financial correlations, first of all, are noisy. And that's why you actually really need to pre-process well the data. As you saw, for example, even in our examples yesterday, when we dealt with the covariance matrix, we realized that when we regularize this matrix in one or another way, we get better performance out of sample in the future. And most of the studies are done just with the, covariance matrix, blah, blah, blah. And it has a lot of outliers, etc., etc., etc. And also there is a moment that correlations, covariance matrix, it explains linear relationships. And relationships can be non-linear. And you can see, for example, if the data, we think that in finance data look like a straight line, but it's not true. The relationship can be, for example, so symmetrical. And symmetry is something what happens in the physics, in real world, and also in the financial relationships. And if you check correlations of this data, it's close to zero. But if you calculate another matrix, for example, mutual information, which is based on the entropy, you can see it's pretty high. So because actually there is a lot of mutual information in this data sample. Yeah, the third thing is the variance adjudication. So basically it explains the data in sample. So basically it's simply not useful for building the strategies. And basically you can just explain the variance in sample. It's simply overfitting. All mathematical models, they're built to overfit. And that is not what you're want to have in real life. While machine learning is actually designed to predict things out of sample. That's how the discipline is. And also, guys, you mentioned a lot of Bayesian models, and you're right, because Bayesian models, they explain the causality, they explain the reasons why things work. And again, such formulas, they don't explain anything. Also, when we define some variables, for example, even this Fama-French model, maybe the variables you got right. So you really can say that the price of some stock depends on the overall market. It depends on the value of the stock. It depends on the size. And actually, it kind of makes sense, right? But when you define the interactions by yourself, for example, Fama-French, they define this as a linear combination. You can define it as like linear combination with some multipliers. But who said that you're right? Basically, that's not the problem. You define the relationships that you kind take from your head. And the financial systems are much more complex. They're hierarchical, they're not linear, and you can't rely on your mind, your linear mind, to develop such models. And yeah, basically you can get even the data right, the variables right, but when you think in an econometrical way, your models are wrong. They're not realistic. Also, p-values. This is what is like statistic 101. Basically, when you check, for example, if your discovery has statistical significance or no, you calculate these p-values, and then you say it's like significant or no. But actually, this is something what is really misused, because they, first of all, as you can see, they require strong unrealistic assumptions. Basically, correct specification, that your variables are uncorrelated, and that noise residuals of your model, again, overfit model, follow normal distribution. This is something what you can't ask in real life. Also, if you have multicollinear regressors, you can't use p-values. And basically, as you can see, they evaluate the irrelevant probability. Basically, you kind of want to neglect the hypothesis zero, but you really want to predict the opposite thing, and why you need to have such complex change in your mind. So basically, instead of calculation of the p-values, for detecting if your variables are significant or no, you actually want to do the feature importance. And this is what we'll, for example, do today. Again, training set overfitting. That's what we saw this slide yesterday, sorry, right? So basically, when we develop the models, we can overfit on the training set, and how we can deal with this, we can work a bit on the data to make it more, for example, resampled or more frequent. We can use ensample methods that help to generalize or regularize the models. And for example, regularization is basically what we did yesterday. And also when apart from overfitting the training set, of course, you have some testing set when you do your like back testing, when you check your strategy performance, but it's also just a single set, and you can overfit to this, because when you have your testing like 10 years, for example, you have 20 years of data, use first 10 years to fit the models, and then you use second 10 years to check the performance. The second 10 years is also some sort of overfit. Because the second 10 years, if you consider the data is random, you just have one realization of the random process. And basically you overfit to one realization of the complex stochastic process, which is also wrong. And we'll talk a bit more today about how to deal with this. And for example, yeah, there can be sample approaches, etc., etc., etc. And in testing set overfitting, for example, yesterday we saw things like deflated Sharpe ratio and probabilistic Sharpe ratio. And yeah, if we want to summarize the difference between econometrics and machine learning, this is a really good slide, because we want to set up a goal, and instead of explaining patterns in sample, we want to predict things. When we visualize things, you also want to visualize complex high-dimensional data. For outlier detection, we also want to work with high-dimensional data. For feature extraction, the same. So basically, this is all what we saw today. All right. What do you guys think about it? Let's discuss it for a while as well. You mentioned that the main problem with econometrics is the linearity assumption of ordinary squares, which is unrealistic assumption in a lot of cases. Can usage of non-parametric econometric methods solve the problem? Yes, it can. It could, but still you can define the model. So here the main problem is that even if you are in the Bayesian framework, you need to define the right model. And that's kind of the problem, because defining models is hard by itself. And that's why, for example, we're living in the age of machine learning now, because machine learning allows us not think in terms of the models, but think in terms of meta models. It's like I have the images data set, and I know that stacked convolutional layers can deal with it. And inside of this like big meta model of hundreds of convolutional layers, it optimizes, it finds the right subset of these layers, right parameters to work on your data well. And but for example, when you do mathematical model for images like SIFT or something, you're immediately biased to super small things. It's not generalizing. So in general, yes, of course it's better to use non-parametric models, but. I'll also check if anything's here. See guys, I also need to check YouTube as well. Download and code from your GitHub, but then still run it. Please run it, it just takes 1 minute to run it. All right. Let's go further then. We reviewed a bit of the econometrics, and we can discuss it even more. But here is another point of view, more not from the problems point of view, but kind of from the evolution point of view. I think you also know that in machine learning, there are like generative models and discriminative models. And for example, we can see that this is the picture from one book I'll also share with you. That basically we see the orange circles are basically about the evolution of the methods of the algorithms themselves. For example, in generative models in pattern detection, basically Bayesian neural networks are better than Bayesian regressions, because it's kind of much more complex structure of data, and Gaussian processes as well, because they're more flexible. Talk about discriminative models. Look, we have some time series models like Rima-Garch, and they're slowly being replaced with their non-linear competitors, basically in form of recurrent neural networks. And when you want to smooth data, also you want to work with maybe with convolutional neural networks. And when you want to find the subset of features that explain the patterns, you want to work with the autoencoders. And this is like, from the algorithms point of view, this is where machine learning is coming to the game. And this is something what is relatively standard in a way. Now let's go to the practice, and now let's do basically machine learning as we used to do it. I'll introduce to a data set. I'm just checking if you see me, guys. So no, you don't care, but for the YouTube, I prefer to be accurate. All this is basic. What about 2 SLS, 3 SLS that could capture the complexity of this? Actually, I don't know what is 2 SLS, 3 SLS, to be honest. I have no idea. Let's check it. 2 stages. Actually, I didn't know. I don't know about this tool. Maybe I just know it with a different name, but what is? Okay, to estimate causal controlled experiments. I don't know, guys. I need to check these methods out because, to be honest, I hear about 2-stage list first for the first time. Regress each column, regress one predictor. So basically, it's some sort of like handmade deep learning, as far as I understand, right? And you also build the hierarchy. I need to check it out, guys. I see that some sort of like 2-step, like also hierarchical representation. Let's check it later. What I wanted to show now is the, first of all, kind of for our own references, what I did, I just Googled deep learning for stock price forecasting, and I checked, for example, this is the paper from the relatively fresh. It's even, see they're like respected members of IEEE. Basically, they show us there can build some recurrent neural networks, autoencoders, blah, blah, blah. I just want to check what is some sort of state of the art we can achieve. Basically, they show that they can forecast different indices with pretty decent accuracy, and they define the features. They also say that, for example, MAPE and correlation coefficients look, they're really very high, on average, like 96% of correlation. So it looks like we should get also something similar, right? And also when I check some blogs, basically in the blogs, they also report some similar good performance also in this blog. So I think that we should get at least something very similar, right? So this is what we will try to achieve as well. The data set I prepared for this task today is basically data set just for one single security. It's for the Apple stock. I also, as you can see, I added a bit more variables. So we don't work just with the prices, but for example, from the close price, I extracted technical indicators from the volume, some stochastic oscillators. Basically, we have market data, we have market features based on the technical analysis, and also some fundamental features. This is our data set. And also to visualize it, we can see that these are the prices, high, low, and also we split like train test already to visualize, basically to see the difference. The volume was basically decreasing with times. And this is the features. Basically, this is all the other features we have. Some of them look pretty random. Some of them have some spikes and patterns. So basically, this is what we got. And what is the normal and, let's say, correct machine learning pipeline? First, we need to prepare the data. We need to normalize it, right? And as we know in finance, the patterns can change with time. So basically, the statistics of the data also can change with time. That's why what I do here, I fit my scaler for the inputs on the trained data, and then I use the same scaler. So basically, when I fit the scaler, I get like statistics from the trained data, and then I don't know statistics in the future. So I kind of, to be correct, I just kind of save in mind, I assume the statistics will be the same in the future. I know it's not really true, but I don't want to overfit for the future. So basically, I use what I know, you know? So test statistics from the train transform it and get it. And the same I do with the Ys. And Ys are basically the close prices, because I want to predict the close price, and I see that the range of the data in the future is different from the past, but I don't know what's going to happen in the future, so I just take statistics from the past. All right, so I normalize the data. I take as the input 2 weeks of all these variables, and I want to predict the price the next day. So basically this way, every day I check the data for 2 weeks behind. I feed them to the model, get the predictions for tomorrow, and if the price tomorrow is higher, I buy it, I long. If the price tomorrow supposedly will be smaller, I short it. And then I just loop over my data set. As you can see, I loop over the data set. This is the window as the input. I take, let's say, last 14 points. Then I take the next point. I made the code flexible, so if I want to make horizon 7, I take like 7 days ahead. Also, I can make the binary prediction if the price tomorrow is higher than now, or I also can predict just the price, and we'll play with the price right now. So I create 2 data sets, and this is, for example, the normalized prices. And then I want to do the modeling. Basically, yeah, in the papers, they talk a lot about some deep learning, blah, blah, blah. But I want to show you that, as I told you, the model doesn't really matter. And I just do very simple multi-layer perceptron. Basically, yeah, I have multi-dimensional input, like 2 weeks by 10 variables, or how many variables? Let's check, or by 16 variables. I just flatten that into the vector, pass it to 1 layer, I apply dropout to regularize the model and predict the price for tomorrow. And basically, I also use the early stopping to prevent overfitting. So basically, the setup looks correct. I normalize the data, I don't overfit to the future statistics, I regularize the model. So basically, I expect to have good performance. Let's just wait a bit for the training. And let's see what it's going to give us. All right, seems like it's already stopped. Also, as you can see, what I do, when I want to check my accuracy, I do the inverse transform. So I go back to the space of the prices, and I calculate the metrics of the mean absolute errors. I want to predict in absolute values how much a mistake is the price prediction, and the R2 score as the correlation metrics. As you can see, my mistake in the price is just $4, which is, I think, not bad, and the correlation is also pretty high on out of sample data. And my image basically also looks not bad. It looks adequate, like all the other papers and blogs we just saw. And then let's do some pseudo backtest. Basically, this backtest is like I calculate some sort of, you see, it's pseudo backtest because I can just transform my prices predictions into the differences. And then, for example, you see if I check, for example, the close price was this, I predicted this, what is the price difference? And if my signal is go short and the price difference is also to go short, I calculate it, I multiply it and get as a benefit. So basically, when the sign differs, it means I'm losing money. When I am kind of good with this sign, I make the money. So for example, here I say, my model says too short, but actually it goes long. So here, for example, I lost money, and here I lost money, here I lost money too, but here I didn't. And there's a pseudo backtest. When I check the performance, what we can see that let's also add some things for the clarity. This is our portfolio networks. I mean, strategy. Label. So basically, I'm showing that strategy HODL is like I just kind of invest in Apple and wait till it grows. And yes, we can see that we even need to calculate the Sharpe ratio, that even with such a nice model, my predictions work much worse than just buying and holding Apple. But why so? I did everything correct. My metrics are good. Regularization, everything is done correct. But this model is not able to trade. And now, guys, the question to you, why it happened so? Meanwhile, you're thinking what happened, I'll try to explain the distinction between generative and discriminative. I am being so a bit in the not slowly, but a bit in the rush, because I'm trying to give a lot of materials, and let's be honest, in 2 days, I can't teach you like how to be the financial machine learning expert, but in 2 days, I can give a lot of basic ideas, and I expect you guys to spend some months or even years learning beyond these ideas. So basically, in a way, I have to be fast in order to show you the whole picture, because I can be slow, I can explain one thing for 2 days, but this way you're not going to see the whole picture. And from my point of view, you go to the summer schools not to learn one single feature, you want to expand your horizon. That's why I'm sorry, but yeah, I know I'm a bit in the rush because I want to expand the horizons of your vision of the machine learning fields. But I'll try to be a bit more precise. What's the distinction between generative and discriminative models? Basically, discriminative model, it's a model that just learns a line, or for example, some surface or some function that just separates the data. It discriminates from class A to class B. Generative model, it learns the distribution, the multimodal distribution that is also it learns kind of the distribution, for example, two classes A and B, it learns two modes, like two Gaussians. It also can separate between these two Gaussians, but it learned to learn the parameters of the Gaussians, first of all. So if you have two Gaussians in 2D kind of as two clouds, discriminative model, it just separates them with the line. And the generative model, it learns the two sets of parameters of the two Gaussians, something like this. One person says overfitting. I don't know what's overfitting, because basically this is the out of sample performance. The metrics are correct as in the papers, basically. I didn't overfit from the parameters point of view. Basically, as I said, I use the statistics from the past, from the future data, both for Y and Z. So if you can maybe expand what do you mean by overfitting. And basically the results look the same as here, or as here, or as here. So basically I can say that from the machine learning point of view, for example, if you had computer vision task, that's what you would do. You would normalize your pixels like this. You would normalize your outputs like this. You would take a model. You would regularize your model with dropout, with the early stopping. You would wait, you would train, you would evaluate on the out of sample data. You would check it, and as you can see visually and in terms of metrics, it's a good result from the machine learning point of view. But in terms of trading, it doesn't work. Yeah, running a bit ahead, did it just repeat previous points? Let's just expand on the idea. So basically, yes, I think I should maybe explain it. Basically, as this model did, and as did, for example, this work of these respected guys, when the black line is the actual data and they show such nice predictions, we can see that both blue and red line, which are the predictions of different models, they're literally just repeating the data the next day. So basically, if you're staying here, all what you predict from your past data is you predict the price from yesterday. The same happens in this block. Basically, so you can see your, so to say, prediction is just the logged data with one day ahead. And the same happens here. And basically this is one of the biggest mistakes why this is a great example why you can't use normal machine learning techniques and approaches with financial data, because the data itself is completely different. It's random data, and random data means you need to prepare it firsthand. And when you have trash in, when you have trash out, the model still tries to find the pattern in this data, right? But when it tries to find pattern in the trash, it finds the trashy pattern. And also when you evaluate it with the wrong metrics, and R squared here is the wrong metric, and MAPI and mean absolute error MAPI are the wrong metrics here, you get bad financial results. So let's expand over this a bit. Why machine learning fails? Why we can't apply it? Basically, as you can see in a nutshell, financial machine learning, it's not equal to machine learning algorithms and financial data. That's what we try to do now, and it simply doesn't work. Here are the different paradigms. Yeah, basically the Sisyphean quants, you know what the Sisyphean work is from the Greek myth, the guy who was like pulling the rock on the big rock on the mountain, and it's kind of like the job that no one cares about. So basically all these researchers that are trying to feed the models the financial data, they publish in their blogs, they publish in their papers, they're just doing nothing in a way. And one of the problems that, okay, let's check what is also happening here. Okay, one of the things that researchers do when they try to normalize the data. Okay, wait guys, I think I want to change a bit the presentation, because I think when I was preparing, I want to do it a bit differently, sorry. Basically, we saw the first slide, we saw the problems in the data. So let's start with doing, you know what, fixing inputs and outputs. So if the data is wrong, and in our case, the data is just like input X and output Y, let's try to fix it somehow. And basically in one of the first slides, I said prices are not pixels. And when we deal with, let's say, normal computer vision things, the gray pixel is always the gray pixel. And the combination of the gray pixels that make form of a car, they almost always mean a car in one another way of a gray color. But if you have the combination of the prices, they literally mean nothing, because this combination of the prices of some values, they are just the samples from some complex stochastic process. And if we simulate, for example, Brownian motion with the same parameters, we can get many random realizations, and each of the small series of the prices is completely random. If we take, for example, this period of data as the input, what it means? Does it mean that after this kind of pattern, the price will go up? No way, it's simply random. Does it mean that after this pattern, it goes up or down? No, it means nothing. And basically this is one of the biggest problem, because we make our inputs and outputs from these samples and it means nothing, it's just random values. The complexity also comes from the thing that different financial instruments, stock prices, options, interest rates, bonds, they can be explained by completely different formulas of stochastic processes. For example, a geometric Brownian motion, we saw before, like normal Brownian motion, also can be geometric Brownian motion. It looks already differently. Merton jump diffusion model, it already looks differently because it allows some quick jumps up or down, as we can see on the picture on the right. It allows with some probability the price to fall down quickly or jump very quickly. And that's what happens in the real markets, and it's already another sort of process. If we want to add the concept of the volatility that is changing all the time, so the variance of the time series can change over time. We have the Heston stochastic volatility model on the left. And this is already different process. And the prices, the samples from this process also mean different things. And on the right, for example, I have the mean reversion model. For example, the interest rates, they follow this kind of process. And these things also means nothing. So it means we can't just take some piece of this time series, extract some features from it, and then use it as the input. And then we can take some piece of the time series in the future and use it as the output prediction, because it is literally trash in, trash out. Also, the idea of forecasting the price of the future, basically this is just explaining of the idea why it's trash, because this is what we, for example, try to do. We simply have no idea what will be the distribution of the price in the future. We have no idea, because, for example, volatility can change, the regime can change, the market situation can change. And forecasting the price itself is, again, it's a trash. It means nothing. It has no value. And that's what we saw in our examples, that when we have trash in, trash out, the model is obviously, but it tries to minimize the error. It tries to optimize something. And the easiest pattern that it finds, which is a trashy pattern, just to predict the shifted time series. That's what we saw. That's what respected people publish in their academical papers. That's what the popular bloggers publish on the blogs. That's unfortunately what I did a couple of years ago and published things like this. But thank God I realized that it's a mistake, and I try to explain people now that don't do this, that is a mistake. But a lot of people did it. I did it myself. And okay, maybe when I did it, I was a student, but we can see people who are publishing papers on IEEE who are doing the same. You see bloggers who have dozens of thousands of the claps on Medium doing the same. So this is the problem. How we can try to fix this problem? Do you guys have maybe one idea how we can turn both inputs and the outputs into something what is more comfortable to work, is more stationary, I would say, it's already a hint, or more static, something that you can rely on in the future? And there is one transformation, but I'm sure one of you already knows. Meanwhile, I answer the questions. Maybe some sort of shift. It makes predictions shifted by 1 day and we're not accurate in price peaks. Basically, that's what happened, yeah. Apple was in great upper trend, so you bought a very low price in the start and growth. But when you were doing predictions, you were buying a little amounts and the price differences were very small. That's not, for example, that's not a problem of the price difference, because basically, if our model is as correct as we expect to, even making the benefit from the small price differences, we still can do this. If you don't take into account the transaction costs, of course, but still, if you can predict even a bit better, you'll get an advantage. What is a good metric to penalize such shifted prediction? I'll upvote it and I'll add it to the notes, because I know such, I mean, I've encountered such metric once, but I need to find it. I don't remember now. So guys, what is the approach that we can use to fix this problem? Because there is one approach, and I'm sure you know it. Basically, how to transform this kind of data and make it more reliable for the future. Guys, I'm sure you know it. So basically, when you have like this kind of random values, and we can rely on what is the transformation. I'm trying to give you a hint because I'm sure you know it. This is what, how many people we have now? We have 60 people watching the stream. Yeah, basically, returns, daily increases, decreases of price. We only need difference of our data. Yes, guys, you're completely right. Basically, that's what we saw yesterday, that all people in portfolio management, they deal with the returns, deal with the differences. So let's try to do this. Basically, this will be our iteration number 1 on fixing the results. But you're completely right. This is what we want to do. Let me share the another screen now. Let's do it consequently. So we change the inputs and outputs first let's change the output and then change the input. So basically I want to show you what happens like iteratively, step by step. So basically let's download the same data. As you can see, let's kind of keep the inputs, let's say, not differences yet. So let's check if maybe we can keep them just normalized in a way. But you can see outputs now, we don't do anything with them, we don't normalize, we just keep it as the row closed time series. And we do the same. And already here, how we calculate the future. We take the price on the horizon minus price today in the last day of the window divided by the last price of the window. So this way, basically, we calculate the returns. And when we do the transform, we already see our outputs at least are the returns, the change of the price in percentage. Let's keep the same model and try to train it. The loss is also decreasing. It's a good sign. Meanwhile, answering some questions. Aren't the transaction costs a big issue in building such portfolios? Of course, transaction costs are a very big and important issue, the same slippages, but let's keep the situation a bit simplified now. We right now care about the modeling part. And of course, when you make the algorithm to put in your portfolio, you want to adjust all possible, let's say, limitations. But right now we need to learn how to model at least first, and later we can do other things. And let's evaluate it. Again, we use as evaluation two metrics, mean absolute error, but now it's the error not of the price prediction, but the error of the return prediction. So basically, we know that we in absolute values, we mistake, but by 1.2% on average, which is, I would say, pretty high value. And our R2 score is already negative. So actually, our idea that we need to fix inputs as well is kind of correct, because we see now we have the correct output, but we still got the shitty input. So our model, okay, trash in something adequate out, so it couldn't fit it. But what happens if you try to run a strategy based on this model? Just imagine we don't know these problems with the financial data. You're just some researchers that we heard about returns from the Econometrics course, but we as the machine learning researchers, which can normalize data as we do it normally in computer vision, for example. When we run our improvised backtesting, what we can see? Sorry, I think I need to add this again. Label equal. So we can see that in this case, neural network strategy even almost outperforms, and at some point it really kind of works better than just investing in the Apple. But guys, it's a new insight for us. We can have actually the incorrect model, not of sample data, but it can get good working strategy. And that's why on some of the slides of the Prado, we saw that backtesting is not a research tool. And this is the really important, and it's like archi-important result for us. We can't do any testing of the strategy when we are failing with the modeling, because you can be lucky, but it's the overfit to the backtest with actually completely random results. You get a bad model, you get a good backtest, but this is not a discovery. This is completely wrong. What we can do now after this, we can try to fix also the inputs. And we can check, maybe we can fix the inputs, and this way we can get a better result. At least we know that it will be correct from the data processing point of view. So I just rerun it. I'll just show you what I changed. So basically now I don't do this kind of normalizing here. I just kind of keep it like this. And as you can see, I apply to columns that I want to stationarize, because some of the columns are already stationary, as you can see. Some of the columns already I prepared in terms of the differences. But the ones I had to change, basically, as you can see now, they all look like different. So now they all are in a way stationary and normalized. And now I do the same modeling. The same neural network is being trained. Now the inputs are fixed. And hopefully we'll get something useful here, but let's see. The loss is again decreasing, but we already saw decreasing the loss. So I would not trust it that much right now. Still optimizing, which might be a good sign. Maybe it's going to some good, nice minima. Wow, it trains for a long time, even early. Okay. What we can see here, guys, the model simply didn't fit at all. So we can see it both from there is some crazy outliers, there is crazy R2 score. So this is like something completely unreliable. But again, if someone who doesn't know much about machine learning, who just decide to trade with this strategy, again, guys, we can have the neural network that in sometimes outperforms the simple investing strategy. And this is, guys, the main problem of financial data science. Until we are super confident in our underlying machine learning model, we have no right to build any strategies, because we can get random results that tell us, wow, we got some discovery, look, the strategy is working, like here, for example, like, wow, the strategy is almost working. At some points, it's even outperforming the benchmark, the simple investing strategy. But this is simply not correct by any means. So what we should do now? The questions. What are your thoughts on Markov switching regression models? Basically, the idea of finding the regime switching turning points is completely correct. We have to do it. We can't have a single regime strategy, but this is like a meta layer that is telling you in what stage of the market you're being to. And yes, most probably want to have different strategies, different rules, different models for different stages of the market. What is the R2 score function returning? I think this is the question to Google, to be honest. This is some sort of, you can consider it as correlation. You say that backtesting is flawed, but is that really backtest what you did? I mean, backtesting is simulating actual trading, not simulating price or daily returns. If the backtesting shows some results of different out of standard time frames, why it's wrong? Basically, what I did, I took the out of sample historical data. I compared the real changes of the market and the real returns with my signals for these returns. Multiplied, and this is, by guys, what we did, for example, yesterday in the portfolio management. We are taking the returns from the market, we are taking the weights of our strategy, multiplying them and getting strategy. That's of course, this is backtesting the historical data. So basically, backtesting is simulating actual trading. It's not truly correct. What backtesting is, okay, I agree that we do simplified backtesting now, but with the simplified backtesting, we can track if we didn't have any transaction costs, if our strategy would be profitable. So basically, if backtesting shows same results on different out of sample timeframes, basically, it will not happen, because if you have different out of sample timeframes, most probably have different performance of your strategy. So this is most probably is not going to happen. Kostya, please, if you can paraphrase your question a bit, because I'm not sure that I understood it well, because I think you a bit mixed up the concepts, but maybe I'm wrong. Please, if you can paraphrase it, would be nice. What are the best measures to build a good strategy? The measures we discussed yesterday, guys, that are the Sharpe ratios, deflated Sharpe ratios, probabilistic Sharpe ratios, drawdowns, information ratios over benchmark, and many, many, many others. How you know that it's incorrect if the business results are good? How you define it? How I even can talk about business results are good if my underlying, the reason of this business results is the shit? Guys, basically, this is not a result even, because if my signals are made by this kind of model, this is just a random result. Basically, I have a piece of random time series, and and that's it. It's not a result at all. The business results are good, and that's what I also said yesterday of one of the slides of the De Prado. Develop theories first, and that's what they're trying to do. When we do machine learning modeling based on some feature, we develop a theory, and our theory of the market is that there are some complicated nonlinear relationships between the input variables and the price change, and how to validate this theory. We need to have a good metrics of the machine learning model, and then we can say, wow, the theory is good, let's check the business results of this theory. But there's also another side of this problem. For example, we can have a good machine learning metrics, but we can have bad business results because, for example, we didn't do machine learning right. So that's why financial machine learning is so hard. That's why quantitative researchers are being paid much more than the guys who recognize faces on the pictures. That's why the best people from the PhD with physics and biostatistics, they go to work in the hedge fund, because this is very, very, very hard. This is nothing like fine-tuning BERT, fine-tuning YOLO, fine-tuning DenseNet, running gradient boosting on the Kaggle. And it's not like I'm trying to brag or something. You can see this is the reality. The best practices from industrial machine learning, from research machine learning doesn't work here. You need to really understand the deep connections between your theories to build right data, apply like machine learning with theoretical understanding, and connect it to the business results. And this is much, much, much more than just fine-tuning BERT. So our focus should be shifted into building the best portfolio, not about future price return predictions. Not completely right. That's what we discussed yesterday. The portfolio is only one part of the system. Basically, you can forecast the price, but for example, when you do something what the forecast the price, this is already called a strategy. And the strategy is another asset to invest in. For example, you can invest, you have the portfolio. and you have the Apple stock in your portfolio, which means that you just put some part of your money in the Apple stock and expect it to grow. What you also can do, you can build a machine learning based strategy over Apple stock that predicts the Apple stock efficiently. So the performance of your strategy over Apple stock is better than investing in the Apple stock itself. So this way in your portfolio, now you put not the Apple stock, but the machine learning based strategy on the Apple stock. And that's for what you want to do, have good future price or return predictions. And you need to do them correct, obviously. If the real data is just one realization stochastic process, why not to test our models on simulative realizations of the process, at least to filter out models that are not working? Obviously, we have to do this. And this is what we saw in the slides. Of course, we need to test and do the back testing and the test of the machine learning models of the simulated realizations. We are not going to do it today because it will require another day of lecture on the stochastic processes of the different assets and different stochastic differential equations that describe these assets, but in the essence, you're right. I mean, when you simulate actual trading, there's percentage returns, which you can use to calculate Sharpe. When you just predict daily sign, it's very different from trading. You don't make trade every day on midnight. You can make trade every day on midnight. Basically, you can. You're not for no one forbids you from to do it. You can predict the difference between today's open price and today's close price. And if it's going up, you invest today in the morning and close today in the evening. That's not incorrect from the ideological way. This simplified. I completely agree it's simplified, but still you can calculate the returns, you can calculate the signals, and calculate the performance of your strategy. It's simplified, I agree. And maybe you don't really want to do it in real life, but it's the 2-day course guide. And my job is to show you the tool set, to show you the concepts. And so you can apply them on your not simplified situations. Because what I see that people understand a bit better how the trades are done, but they apply deep learning on the prices. And that's what we saw here, here, and here. And my job is to show you why this is incorrect, not to teach you how to do intraday trading. So this is this simplified backtesting is maybe not realistic, but it's not incorrect. All right, couple of more questions, and let's move forward. Please give me some feedback. What is not clear? What is clear? I understand that now we are at the point where we see that kind of nothing normal works. And I'm about to show you what things are about to at least work better than what we have now. Again, guys, I didn't give you any promise that I'm going to teach you how to trade with deep learning cryptocurrencies or something like this. I showed you in the slides that this is not the objective for this course. The course is to show you the wide range of techniques and the courses that, that are applied with regards to the financial data. That's what we're doing here. So you go out and you apply machine learning correctly. And how you set up your trading system, it's already a bit out of the scope of this course. So guys, any ideas what we can do next? So basically we see that we can get the data right, but then we get we can have like maybe bad machine learning results. We can have good machine learning results, but the strategy is bad. So where should we move? What is our next direction of the research? Should we again tweak the inputs or the outputs? Should we tweak the models? What should we do? If both econometrics and machine learning fail, which of the best parts to work and how one can make up a sort of a hybrid, conceptually, numerically speaking? Yes, this is something what we will try to do a bit later. And also the next comment about feature importance, more meaningful data. This is also what we are trying to do. But like conceptually, basically we got the inputs that are now like returns of different features, and it's stationary, it sounds correct. We got the same outputs, it also sounds correct. But we see that the models aren't fit. Basically, the model's not working because even if we skip the backtesting part, we see that when we check the performance of our model, it's simply very, very, very bad. It can't predict it. So, and we also realize that we can't do any backtesting before we are really trusting in our model. So what do you think you should do with the modeling part? I'll give you a hint, we still need to work on the inputs and the outputs. One of the things you got guys right, this is the feature importance. So maybe if we have trashy data, maybe we need to remove something. But maybe to add some other features. That's really what we also are going to do today. But this is could work, yeah. Is the good way to use some econometric models to explain some patterns and combine it into ML techniques. Basically, this is like what today is a trend, because you know, classic big hedge funds, they are not ready to quit their econometrical vision. So basically, yeah, this is what they're trying to do. Kind of trying to, yeah, we're still doing factor investing, but we do factor investing with machine learning models. So it's something like what they're trying to do, but still, for example, they might do it as you already saw. So sometimes it's not just enough. Cross-validation, yeah, one of the things we need to do, but cross-validation, okay, it can maybe confirm us that we are wrong, but okay, I'll just go to the slides and we'll work on it. So the idea what I want to show you guys is that actually we can keep fixing inputs and outputs again. And now this is the time for that slide that I want to show before, about 7 reasons why machine learning fails in finance. We already saw this is Sisyphean work. Basically, if we keep experimenting, I'm telling you, just if we keep applying machine learning, better models, better pre-processing, better, deeper models, cross-validation, GANs, reinforcement learning, blah, 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 we will keep doing this Sisyphus work, because we will try to just apply some mathematical tools without actually understanding what we are doing. And that's the main problem. And in this slides, and this is like one of the directions of my course, I want to show you how you can apply correct things to this problem. And first, what we did was called, we did the differentiation of the data. That's what we did. And so we transformed out prices and other features into returns. For example, we have also a feature that's called volume, basically amount of the trades. So we have not just amount of the trades, but how this trades is changing up or down. And this time series is indeed stationary, but who says that the stationary time series is full of memory? This is really 2 different concepts, because when we, as analysts, we are trying to predict the price or something, when we check for example, even when we do the factor investing, we check the value, we check the size, we check the actual value and the actual size, and we have the memory. It was going up, it was going down, etc., etc., etc. So we want to have memory, but when we do apply the stationarity transform, we actually lose the memory. So basically, all we have is just returns, and this is memoryless information. However, it's stationary, and for stationary data we can apply machine learning, but that's a problem. And the question is like, we still want, what we want to do, we want to find some trade-off. We want to kind of still to do the differentiation, but still we want to save information about the trades, right? About the trends, right? So you want to generalize the idea of the returns to keep the stationary time series, but to still keep the memory, so keep the trends and how to do it. So basically, ideally, you want to have some sort of transformation when green is the time series. Blue is the returns. But you can see these returns, they're kind of skewed. They have this small trend. So these returns have the memory. And how to do it, how to measure it, that's a good question. And I'll show you a bit now apart from my slides. Basically, if you take some simple time series on the left, this is famous time series data set of the passengers in the flights. We can do the difference in the classical first or the difference of this time series, which makes the data stationary. And this is the difference operator. That's what you can find in Wikipedia. That's what it does. But again, this makes our data like in a way blind. From the red time series, you can't extract any patterns. It's literally like nothing. It has no patterns. So, and if you make, for example, second order differentiation, you remove even more patterns. So what we want to have some sort of differentiation that has order of less than 1. And actually this transform is possible. It's called the fractional differentiation. And we can transform our well-known operator of the first, second, third order differentiation using this expansion. We can apply order D to B fractional value. We can have D, the order of differentiation, 0.1, 0.5, 0.7. And then when we have, for example, differentiation 0.7, we get situation like on the picture. We still have the differences, we still have the returns, but these returns still have some trends. And having this memory, it allows us to actually capture the trends. This is another example of the Bitcoin prices, where the red is the actual price, green line is the first order difference, dark blue line is 0.6 order difference, and the light blue line is 0.5 difference. And it still returns, but returns with the memory. And this is the transformation which you guys most probably don't know if you work with the normal data. Because this is what's invented exactly to work with the financial tasks. And this is, for example, one of the examples of a simple mathematical tool. It's just this is series expansion. But how it drastically changes the financial meaning of the data. Because in finance, you want to keep the memory to predict things. All right, let's go further with the slides here. Yeah, basically you can, we'll do it in the lab session, so we'll calculate these values. And you can find actually even optimal value for this stationarity. And we can see that, for example, for some of the financial time series, the optimal value is even less than 0.5. But in most of the financial studies, we have just normal returns of the first order, which is D equals 1. And the result is that for decades, like literally for the decades, most financial research was worked on over-differentiated time series that have no memory. So basically we were fitting to something what has nice statistical properties, but has no memory, no predictive value. This is thing number 1. Now problem is the sampling, because when we talk about the financial data and we think about it really deeply, what we have in this data set. Let's open already this notebook. But for example, this is the data, these 5 variables that you can find in like any financial data set. High, low, open, close, and for a given date, for a given day. What it means that inside this day, there were happening several trades, several deals of the participants of the market with regards to this asset. And the open and close, they represent the numbers with what price the trades were opened today and with what price trade closed today. And for example, when one of the participants say that it's not realistic to predict the difference in the day, no, we can have a strategy when we buy asset always in the morning and sell it always in the evening. And our goal is just to predict the difference inside the day. And for example, as you can see, it's always different. And for example, in this case, it would be nice to spot the patterns that tells us we need to short. So the close price in the end of the day, the price was lower than today, and vice versa. And if we can predict this value, we can exploit it, and we can have incomes every day. And high-low, which means the highest price and the lowest price for the day. So we kind of do it daily sampling. We get all the trades inside the day, calculate these 4 statistical values, and okay, that's how we make our financial data. This data has several ideological problems. And also these problems are related to what you guys were saying in the comments, that you're right, maybe you don't want to trade daily. You can trade daily, you still can do this. But you're kind of right that in a way it makes not much sense, because there are days that are kind of calm, and there are days of the high volatility. Maybe there are not days, but they are hours of high volatility, because we're living in the really fast markets. And maybe you want to trade after the IPO happened or after some news was released, and all the activity kind of happens inside half an hour. And this half an hour can be much more informative in terms of the trades, in terms of like the activity compared to 1 week or even to 1 month. So we know that when we sample these 4 values by the days, what we in fact have, we have data samples that have different amount of information inside each other. Some days are calm, some days are full of events, but we still sample daily. And there are different alternatives how we can sample. We can sample by amount of trades. For example, we can say we want to sample these 4 values, not every day, but every million traded on the exchange. Or for example, when the imbalance changed or something like this. But just give you the idea that we can sample the data very differently. And there are many techniques to do this. This is not what we're going to do today, but this is just one of the examples how we can, again, if we understand the finance, if we understand what's happening on the market, we can completely remake our data. We're still gonna have the same variables. It's still gonna be high, low, open, close, but the information deep inside this high, low, open, close will be completely different. Wrong labeling. Okay, so we worked a bit on the inputs. What can we do with the outputs? And for example, what we did, I think it's called fixed time horizon forecasting. So basically we say, I want to predict how the price will change from today to tomorrow, from today to 7 days from now, from today to 1 year from now. And it's called fixed time horizon. We can predict the return, we can predict the binary or ternary classification. So basically, that's what we do. And that's kind of comfortable to the forecasting. But if we really think about the nature of the financial data and nature of the decision-making in finance, even, for example, you do a forecast for tomorrow. But actually, you guys are right. It doesn't mean you need to close the deal exactly tomorrow evening. You might close the deal when you meet your expectations and you're inside the day, the very morning, or 5 minutes before the evening, or something like this. And so basically the idea is that when you make a financial decision, you do make it in the fixed time horizon. You make it, you're really flexible in this. And it depends on the market situation, on the volatility of the market, on some other properties. So basically what you really do, it's like, for example, you make a forecast for the 7 days. It doesn't mean that you buy now and sell, for example, exactly in 7 days from now. You might sell even tomorrow, in 2 days, in 3 days. Because when you make a prediction, you kind of have some target in mind. It's like, I see the situation on the market. I expect it in a week to grow by 10% or fall by 10%. But if it grows, for example, by 10% or by 11% in 3 days, you close the deal in 3 days. You're not waiting till the end of the week. You met your expectation, you took your profit, and you close the deal. The same, you have your own like risk limits. For example, you say, I have this prediction for the week, but my risk limit is I don't want to lose more than 3%. And if, for example, on the day 2, you get this limit of this 3%, you close the deal. You don't wait till the end of the week. And that's how the traders work. So actually, you need to remake your labeling method to correspond to this logic. Because forecasting what will happen exactly in a week from now is simply not realistic. And the method is called triple barrier. It's one of the ways to do it. And basically the idea of this method is that basically you define some window in the future, and you define like 3 barriers. One barrier is in the end of your window. So basically what happens in the end? In the end, price went up or down. But vertical and horizontal barriers are exactly this take profit and stop loss barriers. So for example, if inside this window you touch first the upper part, it means you took your profit. If you touch first the lower part, it means you need to stop dealing. And you forecast not what happened in the end, but what happened inside the window. And you label it differently. And this is like also a very important thing that you will never see in computer vision or NLP or even like regular time series analysis. This is a thing that is only relevant to finance, because this is related to the logic of the people who are developing the strategies. This is something what you're not going to learn on any other course. What's next? There also such a thing that's called meta labeling. This is something that is a bit out of scope of this course, but this is the idea that you can, I think you can better check it by yourself. I don't want to mix too many things. But the thing I really want to mention is the not identically independently distributed samples. Basically, when you work again with computer vision or text or something like this, you expect that in your training data, all of the data samples, all of the inputs and outputs, they are independent from each other. So basically the problem, it may happen, for example, imagine you're working with the medical machine learning, with the blood test. And you make the blood test and just some of the drops of the blood, they mix with the other drops of the blood, and it's like, whatever, who cares, right? But no, you actually care, because when you mix one blood with another blood, your results will be completely wrong. So this spilled samples problem, in biology is important, but it's also important in finance. For example, when you have these inputs, you kind of make the inputs of this in forms of some time series of variables. And when they're highly overlapping, it means that your inputs are basically all dependent on each other. And the outputs are also dependent on the inputs that are dependent, they're mixed with each other. And that's why they need some smart techniques to actually do something with this. Because actually the whole theoretical machine learning, if you check the theory of statistical learning, it requires that the data has to be IID sampled. And we already violate it, because we kind of used to the images and texts where we immediately have like 2 images that are independent. It's like 2 photos of the dogs, but it's not like this in finance. And there are different ways to do it. Obviously, you can't ask me to have all of them independent, because this way you'll have really small amount of the data. But there are other ways to smartly weight your samples by uniqueness. So for example, when you have samples that are very overlapping a lot, you give them a small weight when you're training. So basically you kind of back propagate from these samples with a small weight. And when they're really independent samples, you pay more attention to them, something like this. Also the problems with the cross validation, again, by the very same reason. But this is already also a bit more advanced, and I don't really want to dive into it. But the idea is because of, again, it's related to the spilled samples problem, that you can actually, between your train, validation, test samples, you need to do some breaks, some overlaps, to make them really independent from each other. Because if you do cross-validation and your pieces of data are dependent of each other, it's also a problem. But test overfitting, we already basically saw it even today, that we can have a bad machine learning model that overfits to the backtest, and we need to have some ways to do it. And this is what this, for example, deflated Sharpe ratios, about probabilistic Sharpe ratio, etc., etc., etc. Let's discuss it for a while. Log returns is almost the same as percentage returns. Make correlation matrix to check good or bad features. Basically, we are going to do something really similar today, but a bit more machine learning way. So basically, we're going to check directly feature importance to determine good or bad features. Maybe adding validation as a random rolling window. It will eliminate the problem with prediction being just a price shift and will give us available feature-based predictions. Yeah, this idea makes sense. But basically, we already overcame the problem of prediction being a price shift while predicting or the fixed horizon return, or even better, this triple barrier return, which is even much more smart because we predict directly like what you want to do for trading. So what do you guys think about these approaches? Like some particular questions, or maybe even in general, maybe you don't agree with something. Maybe you are like really seeing like, wow, there are things that are different from computer vision or NLP. Basically how you process your inputs, how you process your outputs, even for example, this IID axiom, I would say. No ideas, no questions, no complaints. It's like really, it's like, or you're shocked, or it's like super not interesting, or something like this. Yes, I see that people like there are less and less people watching already the stream because it's getting different. It's not like how to teach a neural network to do something. I'll wait a bit, I think, because I think this is the crucial part. This is one of the last theoretical parts for today. So if you want me to go again over it, let's go, because this is something what is like relatively fundamental. Basically, it's really different from any other data types, how we need to process the inputs and the outputs. In case of triple barrier, everything comes again to the future price prediction, which is not so accurate and can change dramatically, isn't it? Which time period is optimal for it? No, it's not coming to the future price prediction, first of all. It is coming to basically you binarize this prediction. So if you got this, basically you don't forecast the price here. You forecast or for example, return from here to here if it touches here. And it means that, okay, your forecasted return for this window is, for example, 0.01. Or you forecast, or you can binarize it and say 0 or 1. So exactly, you don't forecast the price, you forecast or the return or the binary variable. And second, it can change dramatically, you're right, but basically that's the random value, it can change dramatically, but you're being very flexible because you are forecasting not something fixed. Basically that's the idea, you are not forecasting the fixed random value in the future. You're forecasting in a very flexible way the expected behavior in a wide window of future events. And this is already much more adequate. and it's much more corresponding to a trading logic. Which time period is optimal for it? Depending on the strategy. This is the hyperparameter you need to choose. If the beta is bad or ordinary, is finding best performance in proxies a potential solution? If data is bad or ordinary is the problem, because that's the data. What's the problem? Because that's the data that everyone has. And it means that it will be really, really hard for you to find the edge so you can outperform the market. Because just imagine you have this prices from the market that everyone has. And you, even your mathematical genius, you created some fractal chaos theory, stochastic thing that maybe can predict something. But that's what everyone, you can bet that there is already teams in the world that doing this. And when you got the signal to enter the market, they all got this signal and go in there. So to be really very fair, what you really want to have is alternative data. But we're going to see today example when you can perform better, even having some interesting mathematical features. But this is something what is not going to give you super big edge long term. Can you elaborate on the input data, please? The structure. What is the input for the single sample? Okay, basically, if we're talking about a bit like big picture, what is the raw data that you have? Raw data that you have is the trades that are just appearing every second, every millisecond. Someone bids, someone asks, and people performing trades, right? Buying and selling each other things, people, robots, and it's happening on some exchange with respect to different assets. What we download from the Yahoo Finance, for example, is the aggregated data. So they collect these trades per day, and they say, the highest price for this asset was this one, the lowest was this one, the open was this one, the close was this one for this particular day. And they have the series of these daily statistics. This is the basic option. What we argue today is that maybe you can sample data, not every day, but based on some, for example, like event-based sampling. Why? Because there can be days without any interesting activity. You can spot the pattern and get the edge. And there are hours when a lot of things happen and the market changes. So that's why you maybe want to sample not based on the days, but based on the activity. So normally you wait from day to day, and inside the day, you calculate high, low, open, close. But maybe you can wait from like by amount of the sales done. And then like, for example, $1 million, $1 million, $1 million. And then, for example, the first $1 million can be traded in a week, but the second $1 million can be traded in an hour. And this way, but inside each of these bars, you get similar amount of information. So what is the single sample? Again, this is creativity. You end up with the series of the bars. What features to extract from these bars? Mean, average, entropy, some statistical properties, autocorrelation, technical patterns, Fourier transform, whatever you want. That's your choice. Today we will see some of examples we can extract, but that's the creativity. That's no one's going to tell you what to do. You will need at least a week further to understand what you're telling us about. Guys, not week. I'm so sorry, but this is the profession where theoretical physicists work in, the PhDs, the doctorates, etc. So this is not for a week. And I'm not trying to scare or something. This is like, it's really complicated. It's really different. I'm super shocked. It's extreme paradigm shift in comparison to normal data science. That's what I'm trying to show you. I'm not sure how old is the presentation with flows you showed us, but I wonder how would it happen that so probably so late people saw these flows. This presentation has, it's 2019 or 2018, something like this. So basically it's what I show you here. It's really very, very recent. It's like something what is in a way state of the art. What are some papers, resources that use ML for finance in the right way? In the end of this lecture, you get the full list. How about LSTM models? LSTM models are, I think they can be a good choice if you, for example, got your bars right, you normalize them right, for example, if you apply fractional differentiation over the dollar bars and put it into LSTM model, you got the chances. It can be the good approach. How about RCNN, temporal convolutional network like WaveNet? It doesn't matter because until you got your data right, the algorithm doesn't work. I'll show you in the end of this lecture the financial tournament, and I'll show you where I am in this tournament. I'm not like in top 1. I'm in top 10%, which is, but I'm kind of lazy because I'm submitting there just a linear model, guys. And then with a linear model, I'm in top 10% of the performers because I got the inputs and the outputs right. And I even kind of don't care about deep learning or something. And I think I'll maybe add some slight non-linearities there, but I think it will be still in the core, it will be linear. And I expect to be maybe in top 5% within a couple of months. So again, algorithms, it's not that important. All right, let me finish also. Okay, so the input is exactly 1 bar, right? But this bar is constructed on different methods, sure, like fixed volume. What if I try multiple bars for a single sample or something like this? Yeah, of course, I'm not saying that the input is exactly 1 bar. I mean, the general time series that you get as the input is the series of bars, right? So for example, you get like 10 years of the data of the Apple stock, and in Yahoo Finance, you got this daily bars. And for example, if somehow you can get 10 years of the raw trades of the Apple stock, you can make your own bars for the 10 years, right? But of course, what you want to have as the input to the machine learning model is not just 1 bar. You want to have some, for example, at least the weekly changes. You want to forecast what is going to happen tomorrow. You want to see the history, right? So maybe you want a week or 2 weeks of history. And we saw in the very first examples today that we tried to put this 2 weeks of history, but it doesn't work because you need to pre-process this 2 weeks of history, right? So we can apply things like fractional differentiation to get stationary changes in these 2 weeks, but with some memory. And then we have, for example, the single input can be 2 weeks of fractionally differentiated time series over the bars. That can be the input, one of the inputs. And you can experiment with many other inputs like this. For example, over this fractionally differentiated time series, you can apply some other transformations. And that's, for example, what we are going to do today. You're going to see that how we take, for example, the chain of these bars, we make fractional differentiation, we do over this some feature extraction, and then we try to do some modeling, and then we can see that we'll have some improvements. In stock prices, we are comparing our strategy with hold, but what is the backtest for the cryptocurrency, for example? Basically, this the benchmark, again, that's up to us. For example, I chose the hold just because it's like some sort you can define really simple. It's like we saw yesterday, guys. For example, yesterday what we were building a lot of different benchmarks, and the benchmark, it depends on the investor's view. For example, some investors, they really want to diversify very well. And for them, I want to have my benchmark diversified portfolio. This is my benchmark. Now try to do something better than this, but still keep it diversified. So I think in cryptocurrency, it's also like, what is the benchmark? Because it depends on the investor. Who are the most investors in crypto world? This is the guys who bought or got in some another way crypto 5 years ago, is growing, they're holding that. And for example, we had a client that basically the person who said, I don't like that my crypto is just, I holding it, I want to make more with it. So for him, the benchmark was holding, and we showed him that basically our models and our portfolio outperforms this benchmark of just equal allocation over the cryptos. So it really depends on the investor profile. I also wanted to show a couple of slides more, basically. One is that, yeah, backtesting is not a research tool. So basically we saw it already that if you want to develop theories, like deep understanding of our data, you want to do, and that's what you're going to do, is feature importance. So basically, this is some sort of like, I guess you guys said, coming back to the classics. It's like, I want the power of machine learning, of financial machine learning. I want the power of this cool pre-processing. I want the power of the machine learning algorithms. I want the power of the right outputs, but still I want to have my factors, you know? And if you perform the feature importance, you know your factors. So this way, when you backtest your theory, you can then know what it depends on, right? So this way you can do like what you used to do with factor analysis. And as you can see, backtesting is, while researching is like drinking and driving. Do not research under the influence on the backtest. So basically, that's also to mention that the result of your machine learning modeling is not a backtest. The result of your machine learning model is a really well cross-validated report about the accuracies, about log loss, about mean squared errors, the distribution of this mean squared errors. And this is where you can say that, like, wow, I'm super confident in my models. Now I will try to backtest with them. And if your backtest, for example, is still not good, you go back and do the whole machine learning research from scratch. And basically, yeah, I think you guys know how the feature importance plots look like. And this is, again, one of the examples from the book of the Prado, where he shows that you can run some methods. And the features like with R, E, and N are the random features, like completely random. In this comparison of two methods, they both rank these random features to the bottom of the list, concretely proving that they're not important. Guys, what I think let's make a break a bit earlier, like 10 minutes earlier. Okay, I'm ready to answer more questions, of course. But what I think is will be better to do, we make a break right now. So we don't mix many things. And basically, because what is left for today, basically the theory is done. We are gonna apply some of the things we mentioned here, and we're gonna see again step-by-step improvement where we apply new pre-processing, we do feature importance, when we extract other features, and basically when we do modeling, and then we will see that we can, on the same data set, we can actually perform better than what we saw before. So I'm here ready to answer questions for the last 10 minutes. But if you don't mind, we can just go for a break, for a bit longer break, and then we're gonna do a lot of practice. Because basically, from my side, the slides, the theory, as you can see, almost done. This is all what left. Basically, they'll be just experimenting and some roadmaps. I'm gonna wait for the questions a bit, but I'm ready for the break. All right, guys, then I'll disconnect myself for a while, and let's meet in 40 minutes, right? Or in half an hour, doesn't matter to me. I'll be here in half an hour, so well, then I'll be ready to start. See you soon. Yeah, I think it's better to wait a bit because there's just 35 people. I'm sure that some people get scared with the material, so let's wait maybe until 45 or something like this, and we can keep going. Meanwhile, I think I can start answering the questions. There was one new. What kind of feature importance do you recommend? Because there are a few options. What do you think about explainable AI and methods in case of financial models? Yeah, basically there is one, so to say, not simplification, but like additional detail when you work with financial data. Because, for example, what is regular feature importance? For example, let's take the most primitive example, some method like, how it's called, the perturbation method. It's like you perturbate the features and you check how performance changes if you perturbate the feature, and if the features that affect the most, they supposedly are the most important. The problem is that in finance, we want to treat these methods a bit more, I would say, probabilistic way, and to focus on the out-of-sample performance. So basically what people do here, basically do the cross-validation. And among the cross-validation on all of the batches, you measure the feature importance on the out-of-sample subset on the cross-validation manner. And then basically you kind of merge this out-of-sample on the cross-validation feature importances and, for example, average them. And this is how you ensure that you have a probabilistic view on the feature importance. So you say, this feature was important, let's say 8 out of 10 folds. So it's like 80% important, something like this. And also this way you focus on the out-of-sample importance. So of course, it's feature importance is important. Sorry for Kalampur, but there is one small detail that you would want to add. Maybe more questions regarding to what we discussed? I try to understand what I'm missing about backtesting here. Have a strategy which A, shows good enough metrics, B, perform better than HODL, C, based not on price data and explainable, D, things like fees are considered as well. Why backtesting is not sufficient here to confirm we don't overfit? What are the other metrics? The main reason why you can't confirm we don't overfit, first thing, and we already talked about it yesterday, deflated Sharpe ratio. Because you arrived to this backtest on a one simple small piece of out-of-sample data, you did numerous experiments to come there. So you were tweaking the parameters, tweaking the metrics, tweaking the models, and maybe you came with 100 iterations to achieve this result, which actually means that your finding might be a random guess. So first thing that you're missing here is the taking into account the multiple trials. This is number one. Second, this one out of sample testing is realization of a complex stochastic process. So for example, if we talk about the stock price, it can follow the jump diffusion model, or for example, Heston like dynamic volatility model or something like this. So the Apple price could go by many other ways, exact ways, given the state of the market. So we can say that your strategy just overfit to one of the billions of possible realizations of stochastic processes. So what you want to do here is to simulate stochastic processes, or with the GANs, or try to resample the data. Basically, this is what we saw. I don't know if it still is in the slides. Let's check again. There was a slide with the different ways to deal with the overfitting. I saw it some time ago. So basically, this is the answer. There are two kinds of backtesting. The backtesting in terms of overfitting of the models and multiple testing. That's where the deflated Sharpe ratio and some feature importance comes into the game. And backtesting to the test data, backtesting to the out of sample, which means that you did all your experiments to fit one small, short realization of the complex stochastic process. That's why if you have a nice backtest on 10 years of out of sample data, it literally says nothing about your performance. It says about your performance in one of the random realization. Which the situation is completely different in computer vision and NLP. Because how do you test performance in the computer vision? You create a really good test set where you put all the samples of the varieties of the cats and the dogs you want to recognize. And basically, the more variety of the cats you have, the more you can ensure that the metrics are right. In finance, this variety can be ensured only in getting the more realization of stochastic process. And this is because the situation is more random. What is your preferred cross-validation technique taking into account serial correlation? What I lately use as a baseline, I know it's something what is not really super sophisticated, but I apply just this purged cross-validation that was on the slides. For example, on Numerai, I apply it, even maybe makes no sense, but still apply it. Basically, where is it? I just use this one. I know there are more advanced way to do it, but I can just stick to this one. Okay, I'll go a bit further, and if you have any questions, I'll answer them. So what I wanted to show you guys now, we have to start finally experimenting with these cool techniques. And I want to start with the fractional differentiation. So here we load the data. And what we want to do here, guys, we want to actually measure what is stationary and what is memory, right? Because the claim in my presentation, in the presentation of the Prado of his book, is like, wow, if I over differentiate my time series, I lose the memory. So I think what we need to do now is to prove this statement and to ensure ourselves that indeed we can have a better way than just calculating the returns. So this is the close price. And there is a known technique to calculate at least to estimate the stationarity of the time series. It's called augmented Dickey-Fuller test. And as any other statistical test, it gives us basically the value of the test and give us the p-value and the confidence values. For example, for I'm 1% confident, 99% confident, 95% confident, 90% confident. And Dickey-Fuller test, the lower is the value, the better. So for example, if you take as input just this time series, we can see that the value of the test is 2.47. But for example, to be 99% confident, you need minus 3.4. To be 95% confident, minus 2.86. 90% confidence minus 2.56. So basically, and we have value which is much higher. So basically, we can confirm that this time series is not stationary at all, which is completely correct. If we take the first order difference, just first order difference, we can see that it is like even more than 99% confident they have stationary time series. So basically, we can confirm. And if you take the cumulative sum of this time series, which will be like kind of make it even less stationary in a way, we have a test statistics higher even than the original time series, which again confirms that the tool we're using is correct to measure the stationarity. This is just some visualization. Basically, yeah, this is what we already measured. I know why I'm repeating here, but never mind. What I want to do next, I want to introduce a very primitive but still logical measure on how we can estimate the memory. So basically, we are claiming that when we differentiate in time series, we are losing the memory of the time series. And in terms of losing the memory, it means that the amount of the patterns, if we differentiate and differentiate more and more and more, disappears. And at least not I think, it's like also following the Prado findings, the most primitive measure we can use is just a normal correlation metric between the original time series and the differentiated time series. So if the correlation between differentiated time series and original time series is high, it means that at least linearly we save memory. So let's check it. I think also, let's first of all, obviously, if we calculate correlation between this time series and itself, we can be sure that the correlation will be 1. But for example, if you check the correlation between the differentiated time series, first order difference, and original time series, you can see the correlation is just around 7%, which by this primitive measure, it means that we'll lose around 93% on memory just making first order differentiation. And if you make second order differentiation, we kind of lose almost everything, as you can see. This is not perfect metric of measuring the information because we can use mutual information, but this is our proxy. This is to experiment, to prove our hypothesis. And again, let's use the ML-FinLab library to use fractional differentiation. And let's, again, I'm just recalculating for the sake of completeness of the explanation. Again, let's calculate the Dickey-Fuller test for original time series for first order differentiation. And now I want to run a test. Basically, I want to run my fractional differentiation with values of D from 0.1 to 1. And see, I create this time series with this order of differentiation, D. I calculate the correlation between this time series and original time series, and I calculate Dickey-Fuller test, this value of original time series, of the new time series. And it will take a while, basically. And what I want to do, I want to find a threshold where I can have basically what I want to do. I want to find a threshold which is where I can have value of augmented Dickey-Fuller test better than 95% confidence of the of the first order differentiation, but at the same time I want the order of differentiation to be less. Basically, you'll see it right now. So for example, look, if I make 0.1 differentiation, it means like almost no differentiation. So Dickey-Fuller test is really high and correlation is also high, right? So this is something like what we save a lot of memory, but it's not stationary at all. What I'm looking for a value that is better than this threshold. So it's lower than this value, but not 0 and 1. So as you can see, I can choose this value. So I can choose D equals 0.7 when I have a stationary time series, because it's even better, as you can see, than first order differentiation, even its order 0.7, it saves 60% of the memory, which is pretty nice for us. And the time series will look with this parameter like this. And if we compare it to original differentiation, you see the difference. It visually doesn't look that different, but clearly the pattern is showing how the trend of price going up and the fractional differentiation is preserved more. So it's literally preserves more memory. And this is basically what we wanted to achieve. And we saved 60% of the memory, but left our time series stationary from the augmented Dickey-Fuller test. So when we're going to do the modeling, maybe it looks like we can use this feature as this transformation as a good transformation. Next thing I wanted to show you is the analysis of the feature importance. Basically, I use just a library shop. For us, it even doesn't matter how it works now. We just know that it gives us the feature importance. And I want to create features, like new features from the fractionally differentiated time series, because I have the hypothesis that if I take fractionally differentiated time series, I can get better properties and hence better features. So basically what I want to do, I take my fractionally differentiated time series, and in a rolling fashion, I calculate rolling mean, rolling standard deviation, rolling skewness, rolling kurtosis, and rolling autocorrelation. How this data will look like? Also for us to have the intuition about the, for example, this is rolling mean by the 2 weeks rolling, right? This is rolling standard deviation. And if we, for example, combine them, it looks like interesting features, right? It has something. We can compare with the skewness, with the kurtosis, and with the autocorrelation. So basically, what we got new transforms from our stationary time series. We expect these transforms to represent different properties of the time series. So basically, we are kind of making statistical factors. So what we want to say that, for example, if the first, second, third, and fourth statistical moments go in one other direction, the price will go up or down. This is our hypothesis. We want to analyze the 2-week distribution of data. And also we add autocorrelation as one of another measure. So the more time series look like itself, maybe it also can give us some interesting properties. And we combine it to the previous features we had here before. Yes. And let's forecast for a bit longer horizon, still fixed time horizons, because we just want to check feature importance for now. This is what we have. And as you can see, what we do here is just, what we do here, we just set up the random forest classifier, and then using the API of the shop library, we just calculate the shop values, and which are basically telling us the importance of the feature. And let's wait 1 minute and we will study the findings. Yeah, it takes some time, but it will be worth it. Yeah, it takes some time indeed. I go back to the questions. Could you please explain more for what ADF do and the cycle in the code? ADF is the augmented Dickey-Fuller test. It is a test that tests given time series for the stationarity. Basically, stationary time series is time series that keeps its mean and standard deviation over time. Basically, that's for example, why we want to do differentiation, because differentiation is a stationary time series. And basically, to check the stationarity as the property, there is statistical test that is telling us if it's stationary or no. And for example, like, yeah, basically this is stationary time series, this is non-stationary, and this is, and we want to work with stationary time series. And what augmented Dickey-Fuller test does, you can check mathematics later. It's not that important at the moment. For us as the users, it gives us confidence values and the value of the statistics. And the statistics, the lower it is, the better. So for example, with 1% of uncertainty, basically, I'm 99% confident that if my value, ADF value, is minus 3.43 or less than this, it means the time series is stationary. To be 95% confident, it has to be minus 286 or less, etc., etc. Our value is 247 of this time series, which is much higher than this values, which means this is not stationary at all. And if you take first order difference, as you can see, the value is very small, which means that it's very stationary. And what we wanted to do in the loop, we were calculating, I was checking different range of the D of order of differentiation, because the hypothesis that we want to find the order of differentiation that is, because we also check the correlation as the measure of the memory. And we see that if you take first order differentiation, D equals 1, we lose 93% of the memory because the correlation is just around 7%. So what we want to do, we want to loop over different options of D from 0.1 to 1, track the augmented Dickey-Fuller test value, so I know how stationary my time series is, and I track the correlation with the original time series, so I know how much memory I save. And I want to find a value that will allow me to keep my time series stationary, at least by 95% confidence. So my value has to be ADF of my fractionally differentiated time series to be lower than this value, but it has to save as more as possible memory. So the correlation has to be as high as possible. And I check here and I found that, for example, with D equals 0.7, the ADF is less than my predefined value, and I save 60% of information, which is pretty nice. Meanwhile, the feature importance. We saw by here that this method finds the feature from the volume, the skewness and the mean of the fractional differential close price, couple of technical indicators, standard deviation, autocorrelation, kurtosis are the most important features. And now, guys, I want to basically make a small confession. Some of the features in this dataset are completely fake. Some of the features here I completely made up, generating random values like normal distribution, uniform distribution, Poisson distribution. I just made them up to show you also as a concept how easily you can be tricked with the results in the financial machine learning, and why it is important to develop theories and not blindly running the algorithms and the backtests. So in this particular data set, the last 5 features are a lie. I didn't get any fundamental features. I didn't get any fundamental data. These 5 features are completely and purely random values. And as we can see, if we did the feature importance beforehand, at least we could find, if we, for example, cut lowest 5 features, we could easily find 4 out of 5 completely random guesses. And if we could cut a bit more, we could leave all fake features apart. And that's the thing. Basically, you can see that you can easily, machine learning always finds a pattern. It can find a pattern even in a trash. That's why it's so important to understand every bit of your data. For example, we see that this dividend is somewhere in the middle. So random forest thinks it's not complete trash, but it is a complete trash. And that's why we need to develop series. We need to understand deeply every feature in our data. And later, after we have like human-based understanding, we have to run quantitative tests and ensure that some of the features are not trash. And actually, if you do this feature importance via cross-validation, as we discussed a bit before, you can cut all the 5 features as random ones. But just we don't have time to run the cross-validation because you see it simply takes some time. But even running just once, we saw that this model found 4 out of 5 features completely wrong. And this is correct. So guys, what do you think about it? But you previously said that p-values don't work here. The assumption of normality of the result. Why ADF is even valid here? Because we don't use p-values for evaluating factor model or machine learning model. We use p-values for evaluate stationarity of the time series, which is a bit different concept. I say that p-values are not a right tool to measure the, for example, the factor model or to explain the behavior of the machine learning model, but measuring p-values for basically calculating the stationarity test is not that illegal. Assumption of normality of the residuals, basically, yeah, of course, we can say that we did something not fully correct, but again, if you guys want to check the stationarity test for non-normal residuals, you can go for it and check it again. This is not the course where I can show like everything like super right. Again, correlation is also not the right measure of the memory. But at least we run a simple test, which is adequate, and it shows us the adequacy. It shows us that we really can find a transform that saves some memory, still is stationary. Of course, if you want to dive deeper in the research, you can find both better measure of information and both better measure of the stationarity. There is no doubts in this. But the concept, at least you understand the concept. If you want, you can replace these 2 formulas with 2 other formulas and do better. Maybe more questions? I want to check again the point with the p-values to show you what I meant exactly by the p-values. If those random features give quite as much info as others do, it also means that this model is not good for this data. Can we use something like weighted models to penalize those things? Of course, we can use, I don't know what you mean by weighted models. I think you mean like doing some regularization. But it's not that, basically, it's not really a flow of the model. This is how the data is, because basically your outputs, our predictions of the returns are also random in a way. That's the point. There is so much, so much noise in this data and so little signal in this data. That's why it's not the flow of the data. And actually the feature importance can change over time. For example, in some days, the sentiment is important. In some other days, the sentiment is not important. A value can work in one market, cannot work in another market. The exposure to the factor, basically the importance of some feature, it changes over time as well. And it's completely normal because markets are changing. People check different things. So that's why it's so easy to overfit to any model to the random data. That's why you need to do this feature importance. You need to do really rigorous feature importance, because it's like that's the nature of the task, and you can't weight the models because you don't know in advance which features are good and which are not. That's why the only way to penalize things, you have to take a risk. You run the feature importance and you simply cut the lower 5 or the lower 10 or the lower percentile. That's how it works. Ah, no, it was not. I think it was, no, it was this. A couple of more questions and I'll go further. I'm just still looking for the answer for the p-value question. I just want to show the exact moment in the slides, but meanwhile I can answer the questions. Yeah, p-values, you're right, they require some assumptions, but basically what this tells us is this is p-value about significance of the ordinary least squares regression models, right? So basically we assume that this OLS model has correct specification, that the regressors are uncorrelated, and noise residuals of the regression results follow normal distribution. The p-values for the stationarity test is completely different thing. We shouldn't mix like stationarity test and the OLS regression. It's different things. And the idea that p-values are something very outdated, they're applied to the modeling of the returns, not the testing the stationarity of the data. On that plot, with feature importance, we could how could we define a threshold for what features are good, what features are bad? Only cross-validation. It's another hyperparameter that we need to find over different simulations, over different cross-validations, etc., etc. There is no like fixed rule how to do it. Is it a good approach to find some noisy patterns in our features and delete them? Basically, that's what we are trying to do with the feature importance. We find the pure noise that doesn't contribute to the predictions and we delete them. Yeah, that's completely fine. I think we can go a bit forward to the experiments again, and please keep asking the questions, I'll answer them. Basically, now we got several more tools in our arsenal to do the modeling. And what I want to show you now, how we can combine all these things together. As always, we load our data, but now we remember, okay, let's suppose we don't, okay, let's suppose we remember in advance which features are bad. Let's say we did some preliminary, let's don't complicate our life right now, so we'll remove them. We found before that for us, optimal value of the D for fractional differentiation is 0.7. So we applied this fractional differentiation. And also, as you can see, I use log prices here just because I want to be in the space of percentage differences, not absolute differences, because it's more comfortable to work with. That's why the time series looks a bit different, just because it's percentage time series now. Now I want to show you that in this book, there are many interesting, let's say, rolling feature to extract. Again, I'm not going to dive into details on this feature. You just I can show you the parts of the book just to be, just to be precise. Sure. Basically, there In the book, there are like a list of many different interesting features, like entropy features, some microstructural features that you can extract. You see some, basically there are some another rolling kinds of statistics from the prices, some high-low volatility estimator where you see, it's not a transform over the prices, but, and basically there are like clear implementations. For us, you can read about it later, but let's just consider that, okay, we made the research, we found some interesting feature. Let's not dive into the features at the moment. So let's extract them. As you can see, some of the features, they look something like also like mean over the fractionally, or mean over the closed price, something like this. This looks also very similar. Another features, they look a bit something like a bit more different. Basically, they also estimate something, but they're similar. Let's just consider that if you found some interesting rolling features that calculate some statistics over the windows. And again, this one. For now, it doesn't matter. As you can see, I create new feature set. Basically, these are the features from the book. I want to have them in one group. And these are the same features we extracted last time. I extract them, and I want to use for now just these features. So all the data is real, there is no fake features and something like this. You can also visualize these features just to, again, to see what they do. For example, this is basically this is the mean value of these things, just to smooth our data a bit. This is that was the minimum values and the rolling minimum, rolling maximum values. So basically, this is also like some helpful statistics to get rolling minimum and rolling maximum, right? To see some divergence of the data. We can check mean value and standard deviation, also in a rolling fashion. So basically, this is the time series we're gonna have. We can also track skewness and kurtosis. Basically, it's the where to the positive or the negative are the prices skewed, returns skewed, and kurtosis is telling about the fat tails. So basically, you also can check where tails are fat, that tails are not fat. So basically, it also can give us the idea how predictable, not predictable time series are. And of course, autocorrelation. Basically, also can tell us a lot if time series look like itself or no. Then we create, again, I didn't want to overcomplicate for us also the backtesting part. So let's still keep doing this kind of like one-day horizon prediction. We know now that this is not fully correct, but this is simplification that we can afford for the learning purposes. So basically, but now we have more interesting, I would say, feature set. We create next day return prediction data set. And let's now don't do any feature importance. Let's assume we don't know it. Let's do the modeling. There is one thing I want to show you. Normally, when you do machine learning modeling, you deal with a sort of randomness, because when you deal, for example, with neural networks, you have random initialization, and you know that every round you train a neural network on the same data with the same hyperparameters, you can get slightly different results, right? The same, for example, with the boosting models or bagging models, because you can sample from your data, and each time you run the model, you get slightly different results. This is a problem, because this kind of, you can say, wow, it's not predictable. That's why what I'm doing here, I'm using the bagging classifier over linear models, and I'll elaborate a bit more why bagging, why over linear model. But I run it 25 times or even like 50 times. It's not that important for now, because I want to get, I know that each of my runs will be kind of random. And for example, when I do it in the real life trading, I'm also kind of afraid that my results will be random. So I want to run for 50 times to get some sort of distribution of my accuracies to understand, maybe I can average these models then, so I can ensemble. Maybe I can estimate my best case, worst case scenario. So let's just clarify, this is not for cross-validation. This is not backtesting. This is not simulation. It's just making the correction in my modeling that I know in advance that my model can get different results when I train. So I define bagging of the linear models. Without explaining too much, I can say, because I want to keep my model simple. As I told you, I don't believe, I want you to show you that even linear things can work really well. But as we saw in the slides, that ensembling of the models can give better performance, right? We saw it. So basically, I want to show you that I want to make ensemble of the linear models. The problem is that I know that bagging has some randomness, so I repeat my experiment over time to kind of know the limits of the randomness. And I do ensembling because it will help me with overfitting, as we saw on the slides. Then, as you can see, I even simplify a bit my training features. So basically, we had 2 weeks as a window of, sorry, 1 month, I guess. Yeah, 1 month of historical data is the window. And what I do here, I take the average for each feature for the month. So if I have 10 features, my input will be just 10 features. And Y-train is the, we know what it is. This is the output, the return for tomorrow. And then I calculate Matisse correlation coefficient as the metric. Because this is like a single measure that can also, as you can consider, as a correlation between the true outputs and my predictions. So this is a good measure when you want to measure the adequateness of your model. And we can see that basically the correlation is 4.5%. It can be the worst of 2.5, the best around 6. Which is actually not that bad. So at least in all the runs, my model was predictive. So it never had negative correlation, because if it has negative correlation, it means I'm worse than random. So my model is always better than random. And let's do our primitive back tests, as we like to do. As we can see, I choose for example, so basically if my prediction is, what is my policy? Basically, if the prediction is less than 0.5, I go short. And if prediction is bigger than 0.5, I go long, basically. That's it. Actually, there is one thing that we need to fix this. I'll say to do fix strategy, and we'll discuss it in a while, what we need to fix here. But blue is the benchmark, and we can see that actually we are kind of not sure how we are. But let's check our actual metrics. So basically what I'm calculating here, I consider then the benchmark result is this. And strategy result is the signal, basically one of the signals is the last signal is the loop. So sharp benchmark is 0.95, strategy 0.99. And with 99% probability, probabilistic sharp ratio tells us that this is indeed better than the benchmark. If we calculate, for example, again, I want to show you how I would do that if all the strategies, since they're random realizations, I might be like, it might be a problem of the multiple trials, right? So I might just be lucky that this strategy got better. So I know that I might be lucky, so I take all these realizations here, calculate their sharp ratios, and I measure deflated sharp ratio. And it tells me this against probability of 100%, this is not the overfit, which is also good. But it has much lower information ratio, and I need to run this strategy for a long time before I can actually use it. What we missed here, obviously, apart from this fixing, and we'll do this fixing, we didn't do the feature importance. So what I recommend us to do now is to calculate the feature importance and rerun the strategy. And as we can see that some of the features from the Prado's book the model considers them like completely useless. And for example, this feature from the product book is also useless, at least on this data set. But what's actually important? Kurtosis, the fat tails, mean value, volatility, autocorrelation. So this kind of give us the understanding that we kind of got it right in a way. So we take the first 10 features, recreate the data set, rerun our experiments, and repeat the numbers again. Zero 4.8% against 4.6%. Well, a bit better. Let's check from the basically this is the benchmark. This is the first strategy, and this is the second strategy. This is much better. And if we check probability of this our new strategy on the important features to be better than the old features, on the old features, it's still 100%. So adding the feature importance, so we did the research beforehand. We understood the features are wrong. We ensured that in the modeling phase, we indeed are better. Our distribution is skewed towards the better accuracies. Our mean is better than here. We're like, so this model is really better. Let's run the backtest now. Only then we realize that even by the backtest, we indeed got a better strategy. And this is the pipeline you guys should follow. This is how it actually should work. I want to check this one thing for curiosity. All right, let's discuss it for a while. So basically, a small recap what we did. All what we did here. We did the transformation of the data which is correct from the financial point of view. We did our research by the books, by knowing our own understanding of the statistics. We extracted correct features. We created a model. We took into account overfitting, so we did ensembling. We took into account randomness of the model, so we did multiple trials. We calculated the bounds. We did, after when we realized that our performance of the model is positive by all the bounds, upper or lower, we did the backtesting. We calculated the number of the backtesting. Then we decided to make a boost of our strategy. We did the feature importance, right? We rerun our experiment. Again, first we ensured that from the machine learning point of view, our strategy is better. And then only we ran the backtest, and we ensured that we are correct, that our strategy is indeed better than the previous one. As you can see, 3 very relatively simple things, but again, you usually don't do this kind of things. We did the super specific transformation, super specific features, and the feature importance with the cutoff. And finally, we got something what we can actually trust in by the confident values, by this probability Sharpe ratio. We can indeed say we found something which is better than just investing in Apple. It's super stupid. Again, we are not taking into account the transaction costs. Maybe if you take into account transaction costs, that this strategy, you fail completely. But if we simplify our world, and for example, we say there's no transaction costs, we just need to find some way to predict movements a bit better than the random. And here I can say we are just 5% better than the random. Our correlation is just 5%. And this is where we can get the edge. And guys, I can tell you that 5% edge is very, very, very good result. basically you will be lucky if you will have 2, 3, 4, 5% of the edge. And this is what gives you the overperformance over your competitors. Let's discuss it a bit, because basically we see we're kind of today we're going to finish relatively quickly. I mean, maybe on your request I can show more things. I still have some materials, but we're kind of very quick. So let's go over the questions. And I think we'll have time for some, let's say, freestyle coding if you're interested, so we can run some more experiments on your demand or your request, something like this. But first, let's really discuss the results, because we kind of did the roadmap from, in a way, stupid, straightforward machine learning to smarter way to dealing with data. And we, by the numbers, we ensure that it's indeed better. Wow, seems like no questions at all. You're shocked. Or you're like, easy, let's trade some crypto. Guys, let me know. I really need some feedback from your side, because you're like 46 people. So, you know, I need some feedback. Looks like we need to have a great prior knowledge of the economics intricacies for us to succeed. That's a lot more valuable than ML experience. Exactly. Financial machine learning is not about machine learning. It's about understanding the nature of the data. And that's what basically what we did in those 2 days. You're like getting so deep into understanding of the data. And basically why it's also important, as I showed in one of the slides yesterday, again, it's all interconnected. What I'm telling here is all around, let's say, the same thing, what they showed in the start. That this is the team. And you can't be just a guy or a girl with machine learning skills to succeed in this. It's simply impossible. You need people who will tell you and explain your financial, because, and also nature of the financial data from the different sources, different markets is different. We took here the simplest examples of the stock market, because it's kind of like, understand, I buy the share of the Apple, I can buy or sell it. It's kind of super easy logic. But there are different instruments, there are debts, there are governmental bonds, there are options, futures, and other structured instruments. And you need to really deeply understand how people trade and what they mean. You need engineers to get the data. You need people who will run the backtests on the scale. You need people who deploy your models. So basically what we do here is maybe even just this and this side. This is really small piece of work. So basically, yeah, in this field, prior knowledge of the, I would say, nature of the data is much more important than running gradient boosting or BERT. Why we use random forest feature import instead of using feature imports from regional models, especially regional models, which is interpretable? It doesn't really matter, because I mean, yeah, it matters. I don't know, just wrote the code like this. Basically, because running feature processing this way, we catch nonlinear dependencies, and then we put features into linear model. So yeah, we can use even nonlinear modeling and do better. Is there any difference in data features for input in a linear and nonlinear model? I want to talk about it a bit later, but that's kind of a thing. For example, how deep learning works. You have several layers of the models, right? And we have this nonlinear transformation. You have layer. In the end, you have softmax, something like this, or some super linear thing in a way, or just sigmoid function, or even just linear output. So basically, you have in the end something what is easy and linear, but before you had a lot of nonlinear transformations. The same here. We can use some interesting nonlinear feature functions and then pass them to the linear decision-making model, which is just a factor model, and we can work well. So I would say that in finance, you don't need complicated models. You want really careful. Just the problem is that to experiment with that, like for example, boosting models or tree-based models, you really need to be extremely careful with the hyperparameters. I need to tune this hyperparameters via cross-validation. And this is like really very long process. That's why I know that with linear model, you just have 1 degree of freedom, which is regularization. So we can run this experiment quickly. But with the tree-based models, it's going to be simply longer and harder, and you need to be very careful. Well, my economics knowledge is enough and I do see the idea, but coding and statistics are completely hard to understand the implementation from the first look. Well, this is quantitative modeling, and what we're doing here is kind of advanced. You see that we are using not standard econometric tools. That's why, yeah, you kind of need to know programming, you need to know statistic mathematics, but that's how you get the edge over the market. So those 005 is our alpha, which comes from a proper feature selection, dealing with randomness, etc. In a way, yes, yeah, that's how we got, we do better than the guess because of the right feature preprocessing with the fractional differentiation, feature selection, dealing with randomness, etc., etc. What's the biggest drawback of a Riemann-Garch model? So maybe models are okay, but data we feed into them is somehow wrong. What is, for example, Garch model? Is the model that supposed to model the, talking about the Garch, model the volatility. What it takes is the input. If I remember correctly, it takes the input some long-term volatility and some short-term linear trends. Basically, this is the econometric assumption. Econometric assumption that says that there's long-term volatility, there is this short-term volatility smiles and clusters, and you model them. The biggest drawback is the model specification, first of all, and model linearity. And again, this model are there, like they have the inputs past volatilities. So maybe you want to basically in crypto, you can model volatility with the sentiment analysis for Twitter, right? But Garch model can't do this. That's the problem. So when you want to model volatility with external features, you can't rely on Garch anymore. The same with Arima. So the biggest drawback is that they rely on the specification that future returns or volatilities, they're like depending on the past returns or volatilities in another way. And that's the model specification bias. Now I understand why trading is harder, more detailed things. But where can we learn about these intricacies? Or is it better to try and found a trading partner with such knowledge? I would really recommend to partner up with a person who is from the financial world. That's what I did, and I definitely don't regret it. It's much easier. Just have a partner who says like, okay, let's go to the German stocks, because this is what happens. This is my idea. Let's implement this algorithm based on this idea. And then I get engineers who get the right data. Then, for example, I or data scientists do the modeling, and we get the strategy. Because I think that each person has to do its job, and it's much smarter to find a partner with such knowledge. I think so. As asked yesterday, how to get started. This part is coming. I left it for the very, very end of the everything. I will show it. And what is the main point for using DNN instead of linear models? Is DNN good for multidimensional data features? Are there any insights on how features can be extracted from other sources like Twitter and use? Basically, again, for example, you have Twitter. But Twitter or news themselves, they're like nothing, just the raw text. You need the understanding of the market and the mechanics of the market to have the idea that you want to use Twitter or for extraction of the keywords or of the sentiment or simply of the, let's say, descriptive statistics, how often some things are happening, or you want to extract the names, or you want to extract some aspect-based sentiment analysis. There's so many things you can extract from Twitter, and what you want to extract, only market expert can tell you. A person who follows the crypto and knows that you know to check the number of tweets from these particular keywords to model the volatility, for example. This is what a modeling expert can tell you. Sorry, market expert can tell you. So insights, you should check for the web pages and the journals where are sitting the financial experts, and they're exploring new factors, new dependencies. What's the main point of using DNN of linear models? Non-linearity. So basically, the patterns are most probably non-linear, and DNNs can catch more complex patterns and give you better performance. With background in econometrics, I already knew about some of the deficiencies and considered the red areas to be the answer. But thanks to your eye-opening presentation, none of them are perfect, and that it's ultimately comes down to data itself. Any works on what to read up on this? The reading is coming, guys. A couple of slides more, and I'll tell what to read. Basically, I prepared a big part on this. I just want to, let's maybe discuss a bit more the experiments, what we did now. So we can kind of close up the part with the experiments and talk about the next steps, literature, and et cetera, et cetera, et cetera. Yeah, but you're right. It ultimately comes down to data itself. Basically, it's like, yeah, it's I even don't know how to elaborate on this more. It's like because we really are used to data that is super clear. Because image, the green pixel is always the green pixel, and the cat on the image is always there. That's why we can build the pyramid of the convolutional patterns. We can even do transfer learning with them, and it works very well. The same as language. The words are always mean the same. The grammatic is always the same. We just need to find the good stacking layers. And lately there are transformer layers. So this is our transformation from the text to the labels. We can even do the transfer learning because the grammatics and the meaning of the words stay the same. So this is simple. And in finance, it's always changing world, always changing dependencies. That's why it's so hard. But that's why this is the multi-trillion industry. That's why for example, people who do the trading, who do the portfolio management, it's not just like, to make more money than the others. It's actually like regulating the relationships of the people. It's regulating the inefficiencies. It's regulating how the market works. It's regulating, for example, the future pension funds of the people who are waiting for their retirements. And it may look like, again, from the media that trading is just about how to easy make money with some robot, but it's much more complex ecosystem. How do analytics approaches change when you move from one investment sphere to others, from trading to asset management, for example? I think that asset management and trading are really highly connected. For example, yesterday, what we discussed, I'll show slides again at this stage. What we discussed yesterday, that there is, where is it? Basically, there is some framework when we want to optimize for some expected risk and expected returns. And basically, for example, if we can have a good forecasts for Apple price and other stocks, that's our expected returns. And we saw yesterday that we can have, when we put into black Litterman, this exponential moving average, which is the better forecast for the returns, we have better portfolio. And the same about volatility. If we can forecast the volatility better, we can have better estimate for the covariance matrix. And also we have better portfolio. So one of the ways how we can use this trading things, we can use this forecasts to have better portfolios. Just instead of having like historical returns or KPM returns, we can inject our predictions and have basically better portfolio. Second way how we can use this, we can say that, okay, I have a portfolio of the assets, but the strategy itself, it's also the asset. Basically, for example, when people sell their own indices, their own portfolios, that's the assets. And for example, when you sell your strategy and you say, look guys, I have a strategy that performs with Sharpe ratio 1.5 with some small drawn, etc., etc. And the person saying, well, I can invest in Microsoft, I can invest in this guy's strategy. And what investor should actually do to estimate the covariance matrix between the stocks and this guy's strategy, and say, okay, I want to invest 80% in the Apple stock and 20% in this guy's strategy. And this guy's strategy, that's what we did today. This is the strategy. And a person can decide, and this is the second way how we can kind of marry this trading thing and the portfolios. Or we can use the forecasts to build better portfolios, or we can build separate speculation strategies as separate instruments and separate assets and kind of use them as just different parts of the portfolio. And then we treat them as another asset. We can calculate the risk, etc., etc., etc. What is the fix of dimension strategy in the last experiment? The fix is that basically, let's do this. So basically, as you can see, that's what this is what my strategy is returning. And I think I'm mistaken the point that, for example, what I said, and this is basically first number is prediction when the price goes down, second number if it stays zero, third number if it goes up. And for example, when I say when the last third number is less than 0.5, I want to go down with the weight of this. And I think this is correct because I want to, yeah, because basically if, for example, there's no fix needed. Basically, if the probability here is 0.3 and it's less than 0.5, I want to go down with this weight. So this is correct. And if in other case, I go up by this weight. So there is no mistake, actually, it's correct. Just I tricked myself. Okay, meanwhile, you're thinking about the questions. I'll go a bit more over the slides because I still wanted to show a couple of more things. Basically, when we talk about the active trading, what else we can do in this field? What else we can do in this field? First of all, we can make another bars, and we already discussed it. Basically, we can have bars that are based on the volume or something like this, and this way we can have better information from the market. Usually it helps. Also, there is one thing that's called filtering. So basically, we saw that problem of the IID, and actually we didn't solve this problem of IID. All our input samples are all intersecting with each other. And one of the ways how you can deal with this, you might want to make decision not kind of on every stage of your trading, but you might want to have first of all some decision making thing that kind of filters all the data and tells you this is the situation in the market when I might want to make a decision or no. So it kind of filters all the situations. It helps solving the ID problem. And also you kind of don't trade all the time. You only trade when it's a good moment to trade. So this is like one of the ideas. Second idea is multitask learning. Basically now we predict just for the returns, and it kind of biases our features when the feature importance of the feature importance only with respect to the returns prediction. And but for example, there can be features that also can be explaining future volatility or other market properties. So if you do the multitask learning, you have several outputs. You can then make your models a bit more flexible, and you make your factors, and you choose the factors from more wide point of view, and usually it helps as well. And third, what you should do is really do rigorous cross-validation backtesting, and I highly recommend you to do is the homework. Basically, take the code, will upload, and for example, apply cross-validation for the feature important to see how it works. To do backtesting on the simulations to see how it works, basically to expand a bit over this work. What are the other research directions? First one, you already talked a bit. This is the instruments pricing. There are some things on the market that are a bit more complicated than just the stock option, the stock share or some interest rate or something like this. For example, what is the option? Option, this is the when you kind of buy the ability. Okay, for example, what you can do, you know that in the future the price of some thing gonna be very high, right?